Hi everyone. In this video, we will be discussing real-valued sequences. This will begin our discussion of sequences and series, which will constitute the remainder of the material for this course. We'll first discuss sequences and series of real numbers before moving on to sequences and series of functions. So to begin, we want to first define what a real-valued sequence is. So a real-valued sequence is a function, A, from the set of natural numbers into R, where sequence terms are denoted as A sub n, and that's just what you get when you plug n into the function A. So as a basic introductory example, we could take A sub n is equal to 1 over n. This would give us the sequence of values. When n is equal to 1, I get 1. When n is equal to 2, I get 1/2. When n is equal to 3, I get a third, so on and so on and so on. Now, you will notice here that I have used the convention that the natural numbers here begin at 1. This is by no means standard. Many textbooks differ in whether 0 or 1 is the beginning of the natural numbers. We want to use the convention that the natural numbers for sequences, our indexes, will begin at 1, really for two reasons. The first is that using this convention, the first element of the sequence is what I get when n is equal to 1, and the second element is what I get when I plug n is equal to 2 into the sequence, so on and so on. If I allowed the natural numbers to start at 0, then the first element of the sequence would be what I get when you plug in 0, and the second element would be what happens when you plug in 1. So there would just be a slight bit of a mismatch. Now, that's not a huge deal. That's just an issue of semantics, but it does make our discussion a bit easier. The second, as you can also see from this example, is if I allowed n to be 0, I'd have to be a little more cognizant of sort of divide by 0 issues. Now, if I was going to start at 0, I could just simply shift this by 1, and then if n started at 0, then I would get 1, 1/2, 1/3, so on and so on. But now notice that I'm getting this by plugging in 0, this by plugging in 1, so on and so on. So again, we will not start our sequences with n is equal to 0. We'll start with n is equal to 1. But again, that's not exactly standard. You'll see a mix of different ways this is done in different textbooks, but this is the convention that we will use. Now, once we have a sequence, okay, we may wish to look at some subsequence. So imagine, for example, I wanted to take this sequence and I only wanted to look at the n values that were, say, perfect squares. So I wanted to look at 1 over 1, 1 over 4, so on and so on and so on. Okay. So I can do that, and the way I define such a subsequence is I pick a strictly increasing function phi from n to n, and then take the composition to form a subsequence. So in this case, what I would do is I would say let phi of k be k squared, okay? And then I would look at, so a sub n sub k would be a of phi of k. Phi of k is just k squared. Plugging that in here, I would get 1 over k squared. So this would just give me the subsequence that picks out all of the denominators that are perfect squares. So this would give me 1, 1/4, 1/9, 1/16, so on and so on. Okay, so this idea of a subsequence is really just a way to pick out certain values of your sequence, but not necessarily all of them. Now, again, notice that this condition that phi be strictly increasing, what that does is it assures that elements will stay in the same order, right? So since this term came after this term in the original sequence, then they must also come after each other in the subsequence. And again, that is enforced by this strictly increasing condition on this function phi. So you have to keep things arranged in the same order. You can't start swapping the orders of elements when you're forming your subsequence, but you don't have to choose every one. So you can just say, okay, I'm going to take this one and then this one, and then a later one, and then so on and so on. But you do have to keep them in the same order. All right. So let's look and think a little more deeply about a couple more examples of sequences. Okay. And in particular, I've chosen these next two examples we're going to look at just to highlight some of the different forms in which we can see sequences and some of the different behaviors we might observe. Now, looking at these two examples, let's compare and contrast them in a couple of ways. So let's first just note that if I look at this first sequence, I can start computing values just by plugging in values of n. So if I plug in n is equal to 1, right, this will give me a negative 1 over 2. If I plug in n is equal to 2, this will give me a 1 over 9. If I plug in n is equal to 3, this will give me a negative 1 over 28. And let's see if I can go one more. If I plug in n is equal to 4, this will give me 1 over 65, so on and so on and so on. Yeah. So first note that this is what we would call an explicitly defined sequence. And it's explicitly defined because I can find, if you ask me what the 50th term was, I could just plug in n is equal to 50 and figure out the 50th term. I don't need to know anything else about the sequence. Okay? This sequence, on the other hand, is a little more difficult to deal with. So the first thing to note is if I look at the way this sequence is defined, the nth term depends on the n minus first term. So it depends on the value of the previous term. So this is what we would call an implicitly defined sequence. Okay, I need to know previous values in order to establish the next value. So that's a little bit different. The other thing we notice here is that actually this all works perfectly fine when n is equal to 2, because then you'll get b sub 1. But what about b sub 1? B sub 1, this says it would depend on b sub 0, but that doesn't really make sense because we're assuming that we're starting our natural numbers with 1, that there is no b sub 0. So what this actually gives is actually a family of sequences where you could look at what happens for different starting values. So we could here imagine, what if I start with b sub 1 is equal to 17? So with that in mind, let's start writing down some of the terms in the sequence. So b sub 1 is 17. Then what's going to happen here? Well, b sub 2, it's first going to depend on whether b sub 1 is odd or even. Well, b sub 1 is odd. It's 17. So what do? I take that value, b sub 1, I multiply it by 3, and I add 1. So let's see, 17 times 3 is 51, plus 1 is 52. Great, that's my b sub 2. Now, b sub 3, it depends on whether b sub 2 is odd or even. Well, here, b sub 2 is 52, so it's even. So I take that even value and I divide it by 2. And so what you can start to see is that what this sequence does is it takes the previous value. If it's even, it divides it by 2. If it's odd, it multiplies it by 3 and adds 1. So this is even, I'm going to divide by 2. This is odd, so I'm going to multiply by 3 and add 1. This is even, so I'm going to divide by 2. This is even, so I'm going to divide by 2. This is even, so I'm going to divide by 2. This is odd, so I'm going to multiply by 3 and add 1. This is even, divide by 2, even, divide by 2, even, divide by 2, even, divide by 2, odd, so multiply by 3 and add 1. You start to notice that now I get sort of stuck in this 4, 2, 1, 4, 2, 1, 4, 2, 1. Yeah. Now, just for curiosity, what if we'd started with a different value? So what if instead maybe I'd started with b sub 1, excuse me, is equal to, let's say, 13. Actually, that one's not very interesting, right? Because if I start at 13, I know what happens, right? So I can already see what happens if I start with 13 here. Okay, so 13, let me first emphasize that one will, whatever happens, it will eventually end up in this 4, 2, 1, 4, 2, 1, 4, 2, 1 cycle. Okay, So let's look at one more then. What if B1 is, say, 15? Okay. So if I start with 15, okay, that's odd. So I multiply by 3 and add 1. That gives me 46, right? So 45 plus 1 is 46. That's even, so I divide by 2. That gives me 23. 23 multiplied by 3 gives me 69 plus 1 is 70. Divide by 2, that gives me 35. Multiplied by 3 gives me 105, and add 1 is 106. Okay, maybe something different's happening here. So now I divide by 2, that gives me 53. Multiply by 3 would give me 159, plus 1 is 160. Divided by 2 gives me 80. Divided by 2 gives me 40. And now you notice, you go back up here, we've already calculated what happens from 40, right? So 40 goes to 20, goes to 10, goes to 5, goes to 16, 8, 4, 2, 1, so on and so on. And now 4, 2, 1 repeats forever and ever and ever. And so you're starting to notice it seems like, well, I mean, we've only tested 3 values, but go try this with some other values. Probably all of the ones you will find, it ends in 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1. So let's contrast a couple things. So one is, if I look at this sequence, these all seem to be approaching 0, right? Here, all of my sequence values are getting, in absolute value, are getting smaller and smaller and smaller. And they're alternating sign, but they're just sort of jumping back and forth around 0, but also getting closer and closer to 0. It seems like this ought to be approaching 0, though I'm going to put a question mark here because we haven't really defined what that would mean. You may have seen this in a previous analysis class, but we haven't yet in this course really defined sequence convergence in a rigorous way. Down here, something different is happening. Like it's not really approaching any one fixed value, but it does seem to be approaching this sort of cycle of numbers. Okay, and it seems like no matter where I start, or at least the cases I picked, I'm going to end up trapped in this 421, 421, 421 cycle. This is a question that we will be able to answer in just a few minutes, right? How can we prove that this converges to 0? This is a standing open conjecture that no one knows how to prove. This sequence is in fact called the Hailstone sequence. For every value, initial starting value that has ever been checked, it ends in this 421 repeating cycle over and over again, but no one has yet been able to prove that that's the case. Every value we've ever tested it for computationally, it ends in this cycle 421, 421, 421, but nobody's been able to prove that, right? Maybe there's some very, very large number, 10 to the 10 to the 10, for which if you start at that value, it doesn't end in this cycle. We just haven't tested it yet. But for every value we've ever tested, it ends in the cycle. It's believed to end in the cycle, but it is an open conjecture. So this idea of convergence, so we're going to call the sequence convergence, right? This is something we'll be able to explicitly define momentarily. We'll be able to prove fairly easily when sequences converge. There is much more exotic behavior, however, that sequences can exhibit. In particular, if you'll notice, this isn't a sequence of real numbers. I mean, it is a sequence of real numbers, but this is also a sequence of natural numbers. All the outputs are natural numbers. And so there's even more interesting behavior you can see here. And these sorts of sequences might be discussed more in depth in a course in, say, discrete dynamical systems. So we won't have much more to say about these, but I do think it's a good example to see, and just to be aware in general that there is a lot more going on with sequences than we will necessarily be covering in this course. It's just that in our study of real analysis, we're really interested in real numbers and in subsets of real numbers, sequences of real numbers. We will be looking only at a small part of that whole area of mathematics. So let's go back then. Let's see if we can make rigorous this idea of convergence. Now, we have a lot of the tools and a lot of the main ideas already built up, right? We've talked about limits before. This is just somehow a slightly different sort of limit. So we will define convergence of a sequence of real numbers as follows. So we will say that a sequence converges to a number L, and we'll write that as the limit as n goes to infinity of a sub n is equal to L, if and only if, for every epsilon greater than 0, there's a natural number capital N, such that if little n is greater than capital N, then the difference between a sub n minus L will be less than epsilon. Now, this ought to look fairly familiar, similar in a lot of ways to our definition of the limit of a function at a point. The real difference here is that we've replaced the delta bits with stuff about this capital N. So instead of for every epsilon there is a delta, now here for every epsilon there is a natural number n, such that now when we were thinking about the limit of a function at a point, we were really thinking about what happens as our x values get close to some point A. Now I want to think about what happens as my values of n get arbitrarily large. So there's a natural number n such that if my little n is greater than capital N, so anytime I go out beyond this capital N in my sequence, then a sub n minus L in absolute values will be less than epsilon. So one way you can think of this definition graphically is, right, we could always plot, say, the terms of our sequence, right? It's a discrete sort of function here. Okay, so you can imagine you went out here and you plotted your function values, and maybe they do something like this. Okay. So you look at this and maybe you have some more data points out here, but I'm not gonna worry too much about those. And so you do this and you think, oh, okay, it sort of looks like maybe I have a limit, right about here. Okay, so you sort of conjecture that this is your limit. And what this definition says is that is your limit if for any epsilon, so the epsilon is how close you need to get to L. So you sort of look in some little epsilon band around L. So again, this ought to look very similar to sort of the picture we drew for functions. So I look sort of distance epsilon up and down from L. And I say, well, if I look in this little band, let's see what happens here. If I go out beyond the second term of my sequence, then all of my sequence values are within epsilon of L. So here, my capital N would be 2, because if I go beyond that, so when little n is greater than capital N, for any element in my sequence beyond the second one, now all of my sequence values are within epsilon of L. And of course, I have to be able to do this for every epsilon, right? So you could choose a different epsilon band, right? So maybe you come back in here and you choose a slightly smaller epsilon. So maybe you choose sort of epsilon in these green bands here, and then that's going to necessitate choosing a different capital N, right? Here I would need to go out beyond the fifth term before all of the terms of my sequence were within this green epsilon band here, okay? So it really is doing the same thing. It's just that this N is capturing the behavior that we really want to look at what happens as n is getting large, right? Whereas with the limit of a function at a point, we're really looking at what happens as our x values get arbitrarily close to some fixed value of the domain. All right, so what we'll see is that the definition is quite similar, at least in application. So let's actually use this to prove that first sequence we saw actually does converge to 0. So imagine I want to prove this limit. Okay. Now, with these sorts of things, it's often helpful to go off to the side and sort of say, okay, what do I want to do? Let me do a little bit of pre-work here. This is not the proof, but it's going to help me write the proof in a minute. So what I want to do is I want to show that I can make a sub n minus L less than epsilon for any epsilon that I pick. All right, so what is a sub n? It's minus 1 to the n over n cubed plus 1. My limit value, I think, is 0, and I want to make that less than epsilon. All right, well, let's see, I can clean this up a little bit. So this is really absolute value of the numerator. Well, okay, minus 0, that 0 can go away. I get a minus 1 to the n in the numerator. Take the absolute value of that over the absolute value of this. Well, if I look at this, minus 1 to the n is either positive or negative 1. In either case, its absolute value is just 1. So that numerator just becomes 1. The denominator, remember, n is always a natural number for sequences, so this thing's always positive. Okay. But really, I just want to guarantee that this inequality holds. Well, if I just do a little bit of algebra here, I'm going to solve this inequality for little n. So if I multiply both sides by n cubed plus 1 and divide both sides by epsilon, I can do both of those because both of those quantities are non-zero. In fact, they're both positive quantities too, so I don't have to worry about my absolute value or my inequality switching. And then I get this is less than n cubed, and so I get that n is greater than 1 over epsilon, sorry, the cube root of 1 over epsilon minus 1. Now, what I've done here in some ways is a little wrong, right? I've started by assuming the thing that I need to show, and then I've backtracked my way to a condition. There is no guarantee that this will work in reverse, right? When I go to back this up, right, eventually I want to assume, like I want to eventually say, this must be my capital N. Okay. And there's no guarantee that this is all going to work in reverse. So this is sort of pre-work. This is sort of a guess. It's a very well-educated guess, but a guess nevertheless. Now I need to write my proof to show that this actually works. Okay. So now when I come over here to write my proof, I say, okay, so I need to show this works for any epsilon. So let epsilon greater than 0 be given. So I'm just going to take an arbitrary epsilon. Okay. Then I'm going to choose my capital N. Now, here's another place I'm going to run into a problem, which is this capital N for any particular epsilon. Well, a couple things. One, it's not guaranteed to be a natural number. And if you go back to that definition, my capital N was supposed to be a natural number. And also, it's not even guaranteed to be positive, right? If I take epsilon, say, to be 3, right? So this would be 1/3 minus 1. That'd be negative 2/3. That's going to give me some negative number. Okay. So one way we fix this is we often say, take this value and round it up to the closest natural number. So this is like the floor function, but like the other way around. And it's, I'm going to use a slightly, oh, sorry. I'll define what I mean by this in a second because it's actually slightly non-standard. Okay. And so this function, it's not exactly the ceiling function, which is what this is often used for, because the ceiling function often just rounds things up to the next integer. What I want this function to do is if x is greater than 0, sorry, so if x is negative, let's start there. If x is negative, I just want this to round it up to 1. Okay. And in fact, sorry, if it's negative, but also if it's anything less than or equal to 1, I just want it to return 1. Okay. Now, if x is greater than 1, okay, this is just going to round up that value. Okay. So if x is 1.5, it's going to round up to 2. If x is 1.777, it's going to round up to 2. If x is 2, it's going to spit back 2, right? Okay, so this is like the ceiling function, but it just takes everything that's less than or equal to 1 and rounds it up to 1. All right, so now if I do this, then whenever little n is greater than capital N, what do we have? Well, let's look at a sub n minus L. Now, a lot of this work over here, this was just rewriting. The first several steps here, we're just rewriting what absolute value of an minus L is. So this is just going to be minus 1 to the n over n cubed plus 1 minus 0. And just doing all that same algebra, I'm going to get 1 over n cubed plus 1. Now, if I substitute in capital N, because I'm assuming little n is greater than capital N, I'm going to put something smaller in the denominator that's going to make the fraction larger. Now, this capital N, it's equal to this quantity, but rounded up, which means that this is less than or equal to capital N. Okay. So I'm going to put something that's even potentially smaller than capital N in here, which is again going to make this larger. Sorry. Get my cube in there and the plus 1. Okay. And now if I simplify this, so cube a cube root, so I'll get 1 over epsilon minus 1 plus 1. Those will cancel. I'll get 1 over epsilon, which is just epsilon. So what I've done here is I have shown that by choosing my capital N in this way, whenever little n is greater than capital N, we have that the absolute value of a sub n minus L is less than epsilon. Therefore, the limit as n goes to infinity of minus 1 to the n over n cubed plus 1 is equal to 0. Limit as n goes to infinity of a sub n is equal to L. Now, you'll notice that in some ways, the only thing that made this complicated was having to do all this rounding business with n. And it turns out that the only reason I needed to do this is because my definition specified that capital N needed to be a natural number. But as you start to think about this a bit, you sort of go, well, if n was a real number, I could always just round it in this way. So maybe I don't actually need that condition. And in fact, you would be right. It turns out that if you can find a real number, capital N, such that this is satisfied, you'll be just fine. You could always make the proof work in exactly this way. So in fact, it's actually quite commonplace to not sort of be too picky about n being a natural number, because if you can find a real number that works, you could always just do this rounding thing to get a natural number. So while this is very technically correct under our technical definition, it would be quite common to do one of the following. So some people would just say, I'm just going to choose capital N to be this. Then I can ignore all of this. Okay. Now, people, maybe that's not great. Some people might not like that, because again, it does say n should be a natural number, but some people would just do this and say, yeah, okay, this is fine. We sort of know what's meant. The other thing that's sort of a compromise is that you'll actually see where people say choose capital N to be greater than this. Now, we know that this can be done because the real numbers are unbounded. That means that we can always choose a natural number that's greater than this real number. And so, we could make this work by just choosing capital N to be greater than this real number. We can always choose, sorry, I think it's because the natural numbers are unbounded. You can always choose a natural number that's greater than this real number. So you could still say, I'm going to choose a natural number N that's greater than this particular real number, and then all of this would still go through. So I point all that out to say, I'm not too picky about how you want to do this. It will all work. You should be aware that there is this technical thing in our definition that says N should be a natural number. But again, if we choose N to be a real number, that's okay. We could still make proofs work. Again, it's something that often in context, people in analysis would not really bat an eye much if you weren't too picky about making sure it was a natural number there, because they know that they could always make it work even if your proof used a real number. All right. Now to finish up this brief discussion of sort of the introduction to some things about sequences, I want to just sort of repeat a few theorems about or facts about convergent sequences. These are each theorems in the textbook, and the textbook includes a proof of each one. I'm not going to fully write out the proofs. I'll just briefly sort of state the result and give you an idea of how you go about proving this, and you can see the text for full proofs. These will be facts about convergent sequences that we will want to use from time to time, but I don't want to spend a lot of time going through and proving them. In fact, I think they are, at this point in the course, the kinds of theorems that you should be able to look at, read, and understand, because they are very similar in many ways to proofs of other theorems that we've seen already. So the first theorem essentially says, if I have a convergent sequence, its limit is some unique number. You can't have a sequence that converges to two different real numbers. Now, the idea is if you wanted to prove this, you prove it by contradiction. So you assume that your sequence converges to two values, say it converges to L and it converges to M. Since it converges to L, you say, oh, well, I can get this, by choosing an appropriate capital N, I can get AN as close as I would like to L. Say I can get that within epsilon over 2 of L. Because AN converges to M, I can get this as close as I would like to M, say within epsilon over 2 of M. So again, I need appropriate N's here. Then I choose my capital N to be the maximum of the two N's from here. And then I'd say, oh, look, this difference, which I could express as L minus A sub N plus A sub N minus M by the triangle inequality. This is less than or equal to each of these. Okay, and each of these is strictly less than epsilon over 2. And so now I've got that L minus M in absolute values must be less than epsilon for every epsilon, which implies that L is equal to M. And so your initial assumption that maybe you were converging to two different values is false because L had to be equal to M. Okay, so this is something that I think I would say we almost never say, oh, I'm using the fact that limits are unique, but you actually are often you use it very often. If it weren't true, it would cause a great deal of other theorems to go wrong. So this is a really handy theorem to have. All right. Now, the next theorem, okay, tells us that if I have a sequence which is convergent, then it must also be bounded. Okay. Now, let's sort of just again to sketch out the idea of the proof here. So imagine you had your sequence A1, A2, A3, and imagine what if it was only like what if there were only 4 things in the sequence? Well, there are only 4 things in this sequence. If it was a finite sequence, you would just say, well, of course it's bounded. It just take the maximum of these 4 things. That's an upper bound for all of the things. Okay. The problem, of course, is if you have an infinite number of things, right? You can't sort of, and maybe I'll come out here and like A99, A100, A101. Okay, so okay. You can't just say take the maximum because, well, the maximum may not exist, right? If you have an infinite collection, it may not have a maximum. So this is where we somehow need to use the convergent bit to help us. So the idea is if your sequence is convergent, then you can get all of your sequence values as close to the limit value as you would like. So what you do is you say, well, I can choose capital N so that A sub n minus L in absolute values is less than 1 for all in little n greater than capital N. Now, what does that allow you to do? So imagine your capital N, imagine it turned out to be 100. We don't know exactly what it is, but imagine it turned out to be 100 here. So for every value beyond 100, that would mean for all of these values out here, these all satisfy A sub n minus L is less than 1, which is the same as saying A sub n is between L plus 1 and L minus 1. In particular, all of these values in this blue box must be less than L plus 1. Well, now, what if I take the maximum of A1, A2, A3, A4, all the way up to A100 and L plus 1? Then the maximum of that whole set, so A1 through A100 and L plus 1, the maximum of that set exists because it's a finite set. It's a set with 101 elements. So that maximum exists. And then what you say is, well, then every element of the sequence must be less than that value. Okay. So you're able here, when the sequence is convergent, to bound the tail of the sequence by whatever you want. And I didn't have to choose L plus 1. I could have put a half here or 5 or whatever I wanted. I just needed some fixed value here to help me bound the infinite tail of this sequence. So that's the idea of this. It is quite helpful many times to have that a convergent sequence is bounded. Notice, however, that the converse is not true. It is not true that all bounded sequences are convergent. So you can take, for example, an easy case of that is just to look at minus 1 to the n. This is bounded, right? These are just negative 1, 1, negative 1, 1, negative 1, 1, so on and so on. So it is bounded, however, it does not converge, right? It never settles down to any fixed value there. So convergent sequence implies bounded sequence. Bounded sequence alone does not imply convergent sequence. Turns out we'll see in a later video that boundedness plus some other property will imply convergence, but we'll deal with that a little later. Okay, so this last theorem, we have that if A is an accumulation point of a subset capital A of the real numbers, then there exists a sequence of values A sub n where each of the values A sub n is in the set A, such that that sequence converges to that accumulation point little a. So the idea here, so I have some set A, and maybe the easiest way to think of this is just as thinking about some, excuse me, open interval. Maybe I'll make it even a union of open intervals. So maybe here, this is our set A, and this point here in pink, this is an accumulation point. Okay, and so what I'd like to do is I'd like to say that I can construct a sequence of real numbers, each of which lies in this set capital A that converge to this point. So the idea is that you're going to choose your sequence. So I'm going to choose A sub n such that A sub n is in the neighborhood of radius 1 over n of A intersect the set A. Now, because little a is an accumulation point of capital A, we know that this always contains at least one point. So I know that I can always choose an A sub n in this way. And by choosing it in this way, it's definitely in A. And so by doing this, the idea really is, so you take a neighborhood of radius 1. So maybe this is your neighborhood of radius 1. It has to intersect this green set in at least one point. Maybe you choose that here, and there's A sub 1. Now you draw the neighborhood of radius 1/2. Okay, maybe that looks like this. There has to be some point in your green set that's within those. So maybe you choose this one, and that's A sub 2. And you keep doing this over and over again, and as these neighborhoods are shrinking down, right, you're forcing this sequence to get closer and closer and closer. So that's the idea of the proof. You can see a fully written out detailed proof in the text, but this is the idea. This is just a handy way when we happen to know something about the topological structure of our set, and we know, for example, maybe that we have an accumulation point. This actually gives us a quick way to say, oh, well, I could have a sequence that converges to that. Now, you might wonder why that would be helpful. Sequences are really ways of approximating a value that you're actually interested in, right? So sometimes it's actually easier to work with an approximation than it is to work with the exact value. And we'll see some cases of that come up in the following material as we continue our discussion of sequences and series. However, that will conclude this video, which has just covered the definition of sequences, the definition of a convergent sequence, worked through an example, and looked at a few properties of convergent sequences.